This video is sponsored by PCBWay. Thanks PCBWay. More of this later. And there I was, hanging around with my good friend Richard on Learn Electronics Repair and chatting around of this little thing. The dot convention transformator setting thing and stuff. And I was there just to bash around for the layout because there were some pet peeves I couldn't get along with. And then Richard came along and said, don't we want to make this a microprocessor project, having some fun with a little CPU on that? And I'm, the idiot that I am, said yes. So that's what we did. And you're probably here because the video on Richard's channel, I'll link to that of course, tells you to go over here to see how the software works. So today we won't do lots of his PCBs. By the way, these are made by PCBWay and they are great quality. But if you want to know what this is all about, you need to have to look at Richard's channel, and I linked to, I think, 2 or 3 videos. We talked about some things in the live stream that we do bi-weekly. This video will be purely software. We don't do any hardware today. This is just software. And maybe we go over to PCBWay and get a PCB made with a new circuit. All right, let's get started. Just a little recap for all the people who have no idea what I'm talking about right now. The idea here is to find out when is the secondary of a transformator in phase or not in phase. For that you pulse a current through the primary and you measure what's on the secondary. The original PCB for that did this with an op-amp and some CMOS chip, and we were going for a microcontroller. Let's go to the schematics to have a short look there. For a detailed explanation of this thing, you want to head over to Richard's channel. There's a little ATtiny. It does all the things, and it pulses something out here, will pulse out, this gets over here, gets controlled by the MOSFET, pulses the transformator. This gets rectified here, we clamp down the voltages, put a little load on it, the pulse gets back into the system, pulls in over here, and the little brain over here decides which of the LEDs lights. This was the fastest version I ever done of this. So let's do some software here, and don't worry. This is easy. This was really easy. This was way more easy than I thought. I was thinking about how do I detect a phase, blah, 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 blah. What do I need to do for that? 50 lines of code with commands. Let's go there. As usual with these projects, you can download the whole project file, so the Arduino IDE, including all cores, including all libraries you need. There are no libraries, I think, and including the source code here directly from the link in the description. I also included a Gerber file, so this is PCB files, I think, where you can make your own PCB with that. You could do this on a Vero board, but I would suggest a PCB. On the schematics, you saw that this is a naked CPU, so there is no Arduino Uno or Arduino Nano around. This is an ATtiny 85. We simply using this because they are pretty handy CPUs and we have them lying around in abundance. They cost about $1.50, I have to check this out, but they're pretty cheap. You need a little programmer from that, and up in the right corner there should be now a link that tells you where you can get a little programmer for that. Of course, I built one, yeah sure. So the Arduino IDE downloads here, this is a 1.8.19, I know, stone old, but still working, is already set up for this. There's the right core for this is the ATtiny core. We selected already the right chip that runs in 8 megahertz, blah, 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 blah. All the mumbo jumbo is already set over here. You don't need to do anything here. Just set your port. Of course, to the right port on your system here. Now, currently, I don't have a programmer connected. And before you do anything else with this chip, burn the bootloader. Yeah, no, up here it says no bootloader. Why should I burn a bootloader when there is no bootloader? When you burn the bootloader for an ATtiny 85, you set some flags for the CPU. So, example, the clock frequency, what are with millis and micros, some brownout detection stuff. Loads of technical stuff. So you need to do this when you get a fresh CPU. Don't forget this. Strange behaviors will occur. After you did this, go to Sketch and simply go upload using Programmer to flash your little CPU. This is the only difference you find from a normal Arduino-ish system. So Richard said, do a short word by for the people so they know what you've written there. And I tell you, this is really the code I written this morning. This is not something that I polished a lot, because it simply works and it doesn't need to do a lot. So let's do this the usual way. Let's imagine us being the CPU and walk through this old stuff over here. We start with some defines. I usually do this because I can't remember these pins. I'm always lost when I'm seeing, okay, which pin was it? And I normally do the define LED, blah, blah, blah. So we only have 4 inputs. There would be some left, but we only use 4 of the little CPU. So there's pulse return. This would be an ADC. There's a pulse send. This is a digital pin. And we have 2 outputs for LED top and LED bottom. After that, we have a delay between pulse and send returns in microseconds. So this would be standing for 20 microseconds. No connection sensitivity. This is just a number 30. This will become interesting when we get the final PCBs made, because currently we were running the whole thing on a breadboard. And you can imagine you're pulsing some 4 kilohertz signals around, and you have all these little antennas on your breadboard. So this was quite nasty. And this won't be that nasty when you have a nice PCB made for that. So we're leaving this in here, and maybe we have to adjust the 30 down here when we get the final PCB. We're not sure about that. If you build this yourself, this is a point where you can tweak the system to detect when there's no connection on the input. So let's have a look. The normal Arduino would run through and look for setup. So setup is over here. Let's have a look. There's something like set default pin states as a function and an analog reference internal 1v1. Let me start with the analog reference. There is, of course, an ADC in the little microcontroller. And normally it uses the supply voltage to detect what's the voltage range of the ADC. With an ATtiny85, you can switch this. You can switch to an internal 1.1 volt reference design. This is primary for battery-operated systems. So you have something where you can go, okay, I have a definitive range, and I can use a simple voltage divider to get my input voltages down to 1.1 volt. So the whole range runs around 1.1 volt. We are going to need this because the both diodes, you maybe remember from the circuit diagram, they will cut down the voltage to 0.7 volt max. So I guess this would be still detectable with a 5 volt analog reference, but if I can do this, I can simply stretch the measurement range here and have a better range. So we're going for the 1.1 internal reference. The set default pin states over here is just the thing that I normally do. You could simply drop it over here into setup. I put the set default pin states over here, and let's have a look. This doesn't do much. It says the pulse return. This is the ADC for input. Not sure if I really need this, but it's in there, so it's in there and it works. Then I have some outputs, so pulse send would be an output. Pin mode for the LEDs would be an output. I set both of my LEDs right to low, so they are not active. This defines all my initial settings, and I don't have to think about that anymore because I simply threw this in and yeah, I'm fine. All right, setup is done. This is a really short setup, and we're already at line 23. So let's have a look what the loop brings. When we were playing around and you watched the video, I was playing around with a tone command. Tone is just normally for generating audio. And you simply say, this pin, I would like to have a frequency of blah, blah, blah on that. The problem with the tone command is this can generate really high frequencies. We're playing around to 10 kilohertz. The downside is I have no idea when the pin goes high and when it goes low. So I was playing this, I thought, okay, do I need to program the timer for that? This is really complicated on these machines. Or is there an easier way? And I went for the easier way. Let's start with these 2 blocks over here. What I'm doing here is simply a toggle. I simply use pulse send, drop it to high, then something other happens, and then I use pulse send and pull it to low. Since this is in a loop, these lines will be called all the time. This will run and run and run and run and run. And it runs about 3,500 times a second. I know this because the frequency on the pin is around 3.5 kilohertz. So let's have a look what I'm doing here. So I'm setting the pin to high. So pin goes high. The MOSFET now pushes current through the primary side of the transformer. Then I wait a bit and you see delay microseconds over here. These are the microseconds that are declared over here, delay between pulse and send return. So I wait about 20 microseconds. This is again a value that came from trial and error. When I did this, I had a scope connected and I knew how long the pulses were, and I didn't want to go right on the edge, but I could tell how many microseconds a pulse would take. So the 20 microseconds are a good value. So you're not on the edge right now where the transformer maybe hasn't switched over, but you're not on the end there. This is somewhere in the first third of the pulse. So this should give us a nice and definitive signal here. And we're reading this already. We're going for an N16 and we read ADC high. So there's a simple analog read, the pulse return pin. So at this moment, we know what pulse we have sent, and we know what the transformer had reacted to, because the ADC high from high over here gets us where this was going. Then I do the same with the pulse pull to low. I wait a bit, read the ADC over here with ADC low from low over here. So after these 6 commands, I have 2 variables, ADC high and ADC low. And these tell me the states on the high pulse and on the low pulse. So the first thing I do after this is this thing over here. This is the detection if something connected or maybe not. So I simply subtract ADC high from ADC low. And it doesn't matter which way around because abs over here. Abs means absolute value. So if I get a negative value, this will automatically convert it into a positive value. So I only get positive numbers after this line. And I compare this to the no connection sensitivity, which we defined over here. No connection sensitivity. So you can tell the higher this value gets, the less sensitivity we get on the inputs. This will get to a point where we maybe run into problems with the final output. But again, this is something for the final PCB to check when it arrives. If this is true, I simply deactivate both my LEDs because this is the case when there's nothing connected. And after I set both LEDs to low, I simply return, so I leave the function and all this runs again. So this is my get out of here function to check if nothing is connected. After this, so at this point, I know there must be something connected. So let's have a look at this. And the final decision over here, which LED lights up, is a pretty simple one. We simply say if ADC low is smaller than ADC high. Arbitrary, if I switch this around, the LEDs simply change place. In one condition, I simply set the bottom LED to low and the top LED to high. In the other case, I set the top LED to low and the bottom LED to high. So the one or the other happening around. And we're done. 47 lines. There are probably smarter ways to do this, but let me tell you, this works. And being the 80-20 guy that I am, I'm fine with that. We have some fine-tuning here, but we can do this after the final PCB arrives. But for this, right now, this is done. Again, I think this is a pretty easy starter project. So if you want to build this, please do. As I said, I would do this on a PCB. So let's head over to PCBWay and let's have a look how you can order your PCB. By the way, from a certain source, I heard that there will be a big event on this site, on the PCBWay site, on Black Friday. They're doing a mixed Black Friday and Christmas event. So you maybe want to check this out. I will surely do. Okay, how do I get my PCB? Because I want my PCB for the little thing over here. You don't mess around with these numbers here. You go for quote now. Then you click on Quick Order PCB. And over here, you simply add your Gerber. These are the Gerber files you just downloaded from the link in the comments. There's my Gerber PCB, transfer, blah, 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 blah. You know, this thing. Let's open this up. By the way, if you want to check if the Gerber is right, there's an online Gerber viewer here. So I upload the Gerber again, go for the Gerbers. If you're just like me and you think, okay, I'm stuck here and I can't zoom out, scroll down and there's a little minus over here that lets you zoom in the PCB and center it in the full resolution. So right now I can check if everything is in place. I can get to the bottom layer here. There's not much going on in the bottom layer spot. This way I have a simple solution to check if everything is in place. So back at your order page, you know you uploaded this thing already. Scroll down a bit. I normally go for a bit thinner PCBs. I normally go for 1 millimeter, not mil. They don't do anything with the price over here. And then, of course, the most important choice, which color should the PCB be in? Green is fine for everything, but normally I go for, of course, black. And you can tell over here, it costs the same, but it takes longer to build. So if you need the PCB fast, for example, for Christmas, you maybe want to stick with the green one because this takes 24 hours. Yeah, now, there are about 1,000 more settings you can do here. You don't need to. You simply go for save to card. So that's all. You simply pay your €5 and your package is on the way. So I'd say ordering PCBs couldn't be much more easy. I wouldn't mess around with a Vero board for that. I simply draw my little PCB and then we order it and then we check it out. We normally go to 2 or 3 iterations depending on the complexity of the PCB, but we always go for a PCB very early in the system. So again, PCBWay is a sponsor of this video. Thanks PCBWay, without you this wouldn't be possible. So while we're waiting for the PCBs to finish up this project and to do the last settings in software, I want to say thank you for Richard from Learn Electronics Repair for having this crazy idea and for asking me out to doing this stuff with him. This is always fun. We learned something there. Watch the video where the both of us stooges hanging around and trying to figure out, will we have a 90 degrees shift in the phase? And this was a funny discussion doing all this stuff. We were hanging out and we simply left the camera running. And I hope you guys will like this because we really enjoyed this. So, I'll see you in the next video. I think there will be one out before Christmas or maybe 2. Well, let's see. So I hope you learned something today and I'll see you in the next one. Bye.